So let's dive into this topic. This one is, so we're going to talk about internal flows. This is flows in pipes primarily. And it's going to build off of kind of what we learned in both topics 4 and 5. And I would say that this topic is one of the most practical topics that you'll, or most, they're all practical, but the most immediately practical topic that you'll see in this class, because we're going to look at analyzing very real world systems and kind of figuring out how much work you need to put into them to get fluid to do what you want. Okay. So basically what we're going to do is we are going to take what we learned about conservation of mass and conservation of momentum. Oh, this should be momentum. And we're going to simplify them for different situations that you might encounter for internal flows. And so those two kind of categories of situations that we're going to consider. The first one is going to be fully developed laminar flow between plates and in pipes. And then the second part is going to consider what if the flow is turbulent. Okay. So for part A, we can use analytical methods, meaning we can use methods that we can work out ourselves with pencil and paper to come up with those equations. But for part B, when we start talking about turbulent flows, we're going to learn empirical methods. So basically what I mean by that is the equations that we're going to use are going to be based on models that have been built up generally based on experiments. So these are models developed based on experiments. All right, so first we're going to review some flow characteristics. And I guess I'm using this word review pretty loosely. Some of it's review, some of it's a little bit new. Okay, so first we're going to talk about what's the difference between laminar and turbulent. If you remember, laminar flow is, very uniform, steady. If the fluid flows in sheets or lamin. Organized layers. And then turbulent flow, on the other hand, is chaotic. I think generally speaking, kind of turbulence versus laminar, you know it when you see it. It's a very visual distinction between the two. You guys did a good job of identifying those differences in homework 1. So hopefully that's pretty old hat. Quantitatively, we can identify turbulence using the Reynolds number. So in the Reynolds number, we of course have density. V bar, this is an average velocity. D is going to be a characteristic length scale. So this would be something like the diameter of your pipe or the distance between 2 plates, for example. And then mu is, of course, viscosity. All right, and we can use the Reynolds number to guide whether or not a flow is turbulent or laminar. And for flow in a pipe, that kind of cutoff number is 2300. So if the Reynolds number is greater than 2300, we consider that flow to be turbulent. And then if it is less than 2300, we're going to say that it can be assumed laminar. Now keep in mind, this cutoff value is for flow in a pipe. 2300 will not be your cutoff number for every situation that exists in fluid mechanics. So if you have flow over a plate, for example, it's going to be a different number. If you have flow over an aircraft, again, a different number. This one's just for flow in a pipe, okay? This average velocity that is in the Reynolds number, we define using the flow rate and then the cross-sectional area. So Q is our normal volume flow rate. And just to remind you, we calculate that by integrating the velocity over area. And then area is just the cross-sectional area. And that's perpendicular to the flow. Okay. Okay, so when we are talking about real world flows and fully developed flows, we have to recognize that there's always going to be what's called an entrance region. So at the very beginning of your pipe, your flow is not going to start off fully developed. It's going to take some amount of distance flowing into the pipe before that happens. And so to kind of illustrate that, we have, I'm going to remind you that fully developed, if you recall, means that the flow velocity does not change along the flow direction. Right? So if you notice in this fully developed region, this profile of the velocity, as we move down the pipe, it's not changing. I have this same parabola that's repeating itself over and over again. So we can say that this is fully developed. But before we get there, we have an entrance region. So this is our entrance region. And this is our transition to fully developed. All right, and so in this entrance region, basically what's happening is at the inlet to this pipe, we're assuming we have completely uniform velocity, right? So that is right here. So inlet is uniform velocity. All right, and then as our inlet velocity, our completely uniform velocity profile is exposed to these walls on the top and the bottom here. If you remember, our no slip condition tells us that the fluid cannot be moving where there's a stationary wall. So anytime our fluid's touching a solid surface, it has the same velocity of it as it. All right, and so what happens is we develop this boundary layer. So that is what this, another color, this line here is a boundary layer. And so what we have kind of developing in this profile is the effect of our no slip condition on the top and the bottom. And so once these two boundary layers merge together, that is where our fully developed region begins, essentially. Okay, I'm not gonna really test you on kind of the ins and outs of this. It's kind of more complicated than I'm explaining at the moment. But that's generally what's happening here, just so that you're aware. Okay, so the amount of time that it takes, or not time, the amount of length that it takes to get to our fully developed region, this is called the entrance length. And knowing something about the entrance length is important because if we want to make an assumption of fully developed flow in a piping system, we want to make sure that the length of pipe we're analyzing is long enough that our entrance length is pretty small in comparison. So we know the stuff that's going on that's complicated at the beginning of the pipe is just a very small part of the overall system. And I'll talk about that more once we get to it. Okay, so if we have laminar flow, the length that it takes to become fully developed is going to depend on our Reynolds number. So you might intuitively realize that how quickly we go from this uniform profile to a parabolic one is going to depend on how big the pipe is, what the viscosity of the fluid is, how fast it's moving. All right, so all of those things are related to each other through the Reynolds number. So we can relate the length that it takes to become fully developed. So this is our entrance length to the Reynolds number. Where we see that this group over here is just our Reynolds number. All right, so I can rewrite this expression and say that the entrance length for a laminar flow is approximately 0.6 times the Reynolds number times D. So D would be either the pipe diameter or the separation between the two plates in our channel. Okay, so recall, we just talked about this, but recall that laminar is Reynolds numbers less than 2300. Okay, so that means that if that's the case, the entrance length is going to be less than or equal to 0.06 times 2300 times D, which is 138 diameters. Okay. Okay, cool. So just keep this in mind. We will use this in a bit. But first, what we're going to do is we are going to get into it for fully developed laminar flow between two plates. Or yeah. No, it's okay. Sorry about that. I got excited. Yeah. Okay, so basically we're going to start from the Navier-Stokes equations, and I'm going to develop the equations that we're going to use for this section. Just as a note for the homework on this and for the problems on the exams, I have no expectation that you're starting from Navier-Stokes and rederiving this. So I'm just going to show you it so you know where it comes from, and you believe me that it comes from these equations, okay? Okay, so the first case that we're going to look at a couple different situations. So the first one is both of our plates are going to be stationary. All right, and I'm going to assume that they are horizontally oriented. So I have my two plates, both of which are fixed, hanging out like this, and they are separated by a distance A. And I'm also going to start off with the assumption that my coordinate system lives right here at where y equals 0 is at my bottom plate. Okay. Okay. And I'm gonna actually take a little segue tangent right now because I think it's helpful. And Owen reminded of me of this when we were just chatting a little earlier. So you may have noticed, or you may not have noticed, but for equations where we're solving Navier-Stokes and conservation of mass, so the topic 4 stuff, essentially all of the variations that you can see of those types of problems are going to fall into either differences in geometry, so horizontal plate versus vertical plates, angled plates. So there's variations with geometry, kind of where your coordinate system is, and maybe how gravity is related to X and Y and Z. And then the other variations that you can see are different essentially boundary conditions. So you might have a plate that's not stationary anymore. Maybe it's moving, or maybe you have an imposed shear stress on a surface. Okay. And those are pretty much, those different kind of subtleties are pretty much the extent of what you guys can handle solving in this class. So those are the different combinations of things that you could potentially see on homeworks or exams and that kind of thing at this point. Okay. All right. So we have our two infinite plates separated a distance A, and we are going to make some assumptions about this configuration. So the first one is that we're going to say this is a 2D flow at most, which means that W is going to be equal to 0, and derivatives with respect to Z are also going to be equal to 0. All right, so we're basically saying this is going to be 2D in X and Y. We're also going to assume that this is incompressible. And I'll just remind you at this point that our Navier-Stokes equations are already written for an incompressible fluid, so we don't have much to do there, but we've got work to do for conservation of mass. We're going to also assume that this flow is fully developed. Can anybody tell me mathematically what that simplification will translate to? Yeah.
The y should be 0.
Not quite. So what direction, X or Y, do you think the fluid will move in? Yes. So fully developed means that in the flow direction, which is X, velocity is not going to change. Okay, so that means that derivatives with respect to X of the velocity are going to be equal to 0.
Question on the 2D. Is it saying that you can't equal 0? I thought that.
Oh, no, it is. I'm sorry. I think I meant to put the slash on the 0 and then.
That's what I thought.
Yeah. No, thank you. That's very valuable. Yes, W0 and dvz is 0. I am also going to assume that this flow is steady. So this means our time derivatives are going to be 0. And then this one's probably fairly obvious, but I'm also going to assume that gravity is only in the y direction. All right. Okay, cool. So let's apply these. The first one is that we have at most 2D flow. So I'm going to get rid of all of the W components of velocity to start, which is a lot. And then I'm also going to get rid of all of my derivatives of velocity with respect to Z. Yeah. Oh, yeah, sorry. Yep. So anything multiplied by 0 is going to be 0. Okay, the next one we want to address is incompressible flow. So like I said, Navier-Stokes, that's already incompressible. So we don't have anything to do there. For conservation of mass, though, that means that density is constant. So we can take it out of the derivatives and divide through by it. Okay. For fully developed, I'm going to take all of my X derivatives of velocity. And keep in mind, I'm not saying anything about pressure, just velocity. All right. And so I'm going to get rid of velocity derivatives with respect to X. So I can get rid of this one, this one, and this one. So anytime you have a derivative with respect to x and it's operating on velocity, we can get rid of it and assume that it's 0. Okay. Okay, now we're gonna get rid of our time derivatives because this flow is assumed to be steady. All right, so our DDT terms all go away. Some of them have already been canceled out for other reasons, but I like to just cancel them out extra so you can tell the reasons. Okay. Okay, and then last but not least, we have gravity only in the x direction. So that means that gy and gz are 0. So I'm going to get rid of those as well. Okay. So yes. Ah, yes, thank you. Sorry. Gravity is in y, not x. Yeah.
If you're starting from y equals 0, then isn't that mean your gravity is positive?
No, so gravity goes like this, right?
Oh, you're not thinking it.
I am not. No, so if I wanted to write gravity positive, then I would do y like this. Does that make sense? Okay, cool. This one goes away. There we go. Okay. Okay, so this is the point where we say, all right, we have made things dramatically simpler, but still not solvable for conservation of momentum. So we still have a nonlinear term. So this term and this term, these are both nonlinear. All right, we cannot solve this system, at least with the tools that we have at the moment. So what we're going to do next is we are going to look at the simplified conservation of mass equation, which looks like partial v partial y is equal to 0. All right. V could be a function of x, y, z, and t in general. But we said this is a 2D flow, so z goes away. We said it was a steady flow, so it's not going to depend on t. And then we also said that it was fully developed, which means nothing changes in the x direction. So we have that velocity is just going to be a function of y. So I can turn my partial derivative into a total derivative. Okay, so I have dv dy is equal to 0. And this just implies that v is a constant, right? Whenever we want to figure out the value of a constant, especially when we have a spatial derivative in here, which is why we have the constant, we're going to need to use a boundary condition to sort that out. So let's go back to our drawing. Velocity in the y direction, v is going to look like this direction of velocity, right? And so as how we normally do for our conservation of mass for these types of problems, we're going to say, well, our wall is impermeable. So that means we can't have any velocity going in or out at the wall, which means that v has to be 0. And that's because the walls are impermeable.
So. Impermeable. So UV or W can be impermeable depending on what your conservation is kind of tricking out to.
Yeah, so it'll be UV or W depending on kind of the geometry of your problem. So if you had walls like this, then U would be equal to 0 for impermeable walls. Does that make sense? So you would draw like the direction that's perpendicular to the wall, which is the X direction. So you'd say U is 0. Does that make sense? Other questions? Okay. Well, V equal to 0 is rather handy for us. And I can use this to simplify momentum even more. All right, so anywhere V appears, I'm going to get rid of that term because V equals 0. I'm writing this in here because I realized that the like salmon color looks just like the red. All right, so all I've done is I've said, okay, conservation of mass tells me that the y component of velocity must be 0. So I can simplify my momentum equations a bit more. Does that feel okay to everybody? Okay, great.
Just a question about you. Throw the equation. Well, that's crossed out too, right? Is anything else in the parentheses crossed out?
I'm not sure that I understood your question. Can you say it again?
So for y, the second row.
This equation.
Yeah. The
Okay.
U outside of the parentheses.
Yep.
That's also 0.
So viscosity is not 0, but we have viscosity times 0. So that whole term goes to 0. Yep. So the question is this term here, do we keep the mu? And technically mu is still there. So this term is mu times 0, which is just 0. Yep. Same thing with the density on the left-hand side. So density is not 0, but it's multiplied by 0. So we just don't care about it anymore. Okay. Okay. So I am going to write down our simplified momentum equations. All right, so our y direction equation, or I'm sorry, let's start with x. So our x direction equation gives us partial p partial x is equal to mu d dy du dy. So I've just moved the pressure gradient over to the left-hand side because it was negative. Is all I've done here. And then I've also leveraged the idea that our derivative is a total derivative with respect to y for the same reasons we just talked about when we did conservation of mass. All right, and then our y direction equation is just minus rho g minus partial p partial y is equal to 0. This is just our hydrostatic equation. That's another thing that you should kind of keep an eye out for as like a sanity check. So if you have completely horizontal or completely vertical plates, actually, sorry, just horizontal. If you have horizontal plates, you should expect to get the hydrostatic equation back in the y direction. Okay. All right, and then our z direction equation is quite boring. We just have that partial p partial z is equal to 0. So pressure is not changing when we move into or out of the board. All right, that should hopefully make some intuitive sense because there's nothing really going on with the flow that would cause that to happen. Okay. So since our x direction equation is the one that is going to provide us an expression for the u component of velocity, let's solve that one. So all I'm going to do is I'm going to separate variables and integrate. And I'm going to do that twice. Okay, so I have partial p, partial x, and I'm going to move my viscosity over here. And then I have d dy is equal to the differential of du dy. And I'm going to integrate this. Okay, so when I do this, I get 1 over mu partial p partial x times y plus a constant of integration is equal to du dy. And I'm going to separate variables and integrate another time. So I have 1 over mu partial p partial x times y plus c1, that whole quantity, times dy is equal to du. And then I integrate. When I do that, I get 1 over 2 mu partial p partial x y squared plus c1y plus c2 is equal to u. This looks like a y. I don't like that. U. Okay, there we go. Any questions so far? Okay, so we need to use our boundary conditions to find C1 and C2. All right, so we have 2 flat plates that are not moving, which means that U is going to be equal to 0 at the top and the bottom plate. So this happens at U equals 0 and at at Y equals 0 and Y equals A. Right? Okay. So let's apply this one first. So if y is 0, I have 1 over 2 mu partial p partial x times 0 squared plus c1 times 0 plus c2 is equal to 0. So this means that c2 is equal to 0. All right, so we got rid of this guy. And the next one we'll do is our second condition here. So now we're going to plug in y equals a. So we have 1 over 2 mu partial p partial x times a squared plus c1 times a is equal to 0. So I've kept that c2 is 0 here. Is that legible? Do you want me to do a darker color? Okay. So I have 1 over 2 mu partial p partial x times a squared plus c1 over a is equal to 0. All right, I'm going to divide this through by a and then move my first term over the right-hand side. So I have that c1 is equal to 1 over 2 mu partial p partial x times a. All right, so now we have C1 sorted out. All right, and so I can plug these back in, and then I have my final expression for u. So I have 1 over 2 mu partial p partial x times y squared minus a times y. All right. And this is our final answer with a slight asterisk. So this assumes this assumes that y equals 0 is at the bottom of the plate. Another common assumption that you can make for your coordinate system is to say, I'm going to put y equals 0 at the center between the two plates. So if instead I said, how about this is our coordinate system. So this is our alternate coordinate system. Then all that we would have to do is just reevaluate our boundary conditions at those different y values. So if we assume y equals 0 is in the center, we just have to redo the boundary condition part. And essentially we have that u is equal to 0 at the location of the plates, which in this coordinate system would be minus a over 2 and positive a over 2. If you do this, which I trust you guys can handle the algebra if you want to do it, what you end up with is 1 over 2 mu partial p partial x y squared minus a over 2 squared. Okay. So this is the other version of the exact same solution, assuming y equals 0 is at the center line. Okay. Okay, so like I said, you don't need to redo this derivation every time you're doing problems from this section. You can start with these. That's completely fine. A couple other things that you will need to have at your disposal are the shear stress distribution. So tau yx is just the viscosity times du dy. Which in this case is mu times d dy of 1 over 2 mu partial p partial x y squared minus ay. So you have mu times 1 over mu partial p partial x. Actually, I'll keep the 2 out front here. And then you have 2y minus a. I'm going to cancel out the mu's. And then this results in partial p partial x times y minus a over 2. Okay. Another handy thing that you may need to know is the volume flow rate. So that is just Q is equal to the integral over the area of V dot dA. So we're going to integrate from 0 to A of U times L dy. So this is our Z direction depth. Usually this is written as the volume flow rate per depth. So I'm going to just divide through by L here. And this integral works out to be 1 over 12 times mu minus delta P over L A cubed. Or I can simplify this so I have a negative times a negative, so I get a positive. And then I'm just going to group this all together as A cubed times delta P over 12 mu L. So this delta P over L, this is P2 minus P1 over L X2 minus X1. So this is just our pressure gradient. So this is our partial P partial X. So if you measure the pressure in 2 locations, you can find the pressure gradient by just calculating the slope of the pressure between those 2 points. Does that make sense? Okay. All right. Any questions on this so far? Before we can do an example. Okay, cool. So that was kind of a review of unit 4, I guess. Yeah. Oh, I'm sorry. Too fast. Okay. All right, let's do an example using these results. So we're going to do some analysis of leakage flow past a piston. So in this problem, we have a hydraulic system that operates at a gauge pressure of 20 megapascals and 55 degrees C. The hydraulic fluid is SAE10W oil. And we have a control valve consists of a piston that's 25 millimeters in diameter, and it's fitted to a cylinder with a mean radial clearance of 5 thousandths of a millimeter. We want to determine the leakage flow rate if the gauge pressure on the low pressure side of the piston is 1 megapascal and the piston is 15 millimeters long. All right, so let me just draw a picture of what's going on here first. So here is a cross-section view. What I'm drawing right now is the cylinder. And then our piston is in here like so. And we know that the length of it is 15 millimeters. We have a pressure 1 on one side is 20 megapascals. And a pressure on the other side of it is 1 megapascal. Both of these are gauge pressures. So I'm going to put a little G up here to remind us of that. And then we also have this clearance gap A, which is 0.005 millimeters, right? And our diameter here, this is D, is 25 millimeters. All right, so this is kind of our side view. If I draw a top-down view, this is circular, right? So I have my piston. So this is those walls that I drew in the first image, but this is the top-down view. And then we have our piston in the center. And here's our diameter D. And then this gap between the piston and the cylinder is A. Okay, so what we are looking for is the leakage flow rate. Which is just Q. And so what we're going to do is we're going to make an assumption. And it's going to be the same assumption that we used in lab 1 with our viscometer. So we're going to assume that since this gap between the plates is really small compared to the diameter of the cylinder, that we can approximate this as a flat plate. So since A is very much smaller than D, we can approximate the space between cylinder and piston as 2 infinite plates. Okay. So I'm going to draw our infinite plates, and we have that the spacing between them is A, and they're both going to be fixed. All right, so this is our first assumption. Our second assumption is that we have an incompressible fluid. That's reasonable because it's oil. We're also going to assume that the flow is steady and that it's fully developed. To check for fully developed whether this assumption is reasonable, I'm going to look at L over A. So this is 15 divided by 0.05. This is 3,000. All right, if you remember kind of in the beginning of when we started this, we had that expression relating the entrance length over diameter to the Reynolds number. And that value was like, what was it, 300 or something? No, 138, okay? So since this is much bigger than 138, we can say fully developed is a reasonable assumption. Does that make sense? So that comes from here. So before we said, okay, our entrance length is where the region before it gets fully developed. And for a laminar flow, it's going to take 138 diameters until it becomes fully developed. So the idea is if the length of where we want to analyze is a lot bigger than that, is part of it not fully developed? Yes. But is that a small part of it? Also yes. So this is okay. We can say, all right, that first 138, we'll just ignore it because the whole system is 3,000 long. So 138 out of 3,000 is a pretty small portion. Okay. All righty. the other thing that we need to kind of look at here is our plate width. So our plate width is L, and this is just the circumference. So we have pi times D. And I guess I should draw this a little more explicitly. This is going to be our length L. And then we're going to assume that we have P1 and P2 on these sides. Okay. So essentially what we're doing is we are taking a look at this. So I've drawn this here, and then the depth of this into the page, if you imagine you took scissors and kind of cut this open and unrolled it to make it flat plates. I know it's a little bit of mental gymnastics. So that's kind of what we're doing here, okay? Okay, so we already have the equation for Q over L that we want to use. So this is A cubed times delta P over 12 mu L. All right, we're given all of this stuff that we need, but I'm going to write out L specifically here. So I have A cubed delta P, and then I'm going to multiply L up here. So our length or our plate width is pi times D. And then we have 12 mu times L. All right, so we were given L is 15 millimeters. Our diameter is 25 millimeters. Pi we know. Delta P we can figure out because we're given P1 and P2. A we're also given. And then mu we can look up for the oil. Because we were told that it's SAE 10W oil. And that is, oh, and it's at a temperature of 55 degrees C, which is 0.018 kilograms per meter second, which means that we have everything we need. All right, so I'm just going to plug that in here. So I have Q is equal to pi. No, let's do A first. So A is 5 times 10 to the minus 6 meters. I'm converting everything into meters from millimeters. This is cubed. Times delta P is 20 minus 1, 10 to the 6 newtons per meter squared. Divided by, times pi, and then times D, which is 0.025 meters. All of that is divided by 12 times our viscosity, which is 0.018 kilograms per meter times second, times L, which is 0.015 meters. All right. And when we use our calculating device of choice to carry this out, we get 57.6 cubic millimeters per second. The last thing that we want to do is make sure that assuming laminar was valid. Okay, so we have a volume flow rate, so we can back out what our velocity was and then figure out our Reynolds number to check. Okay, so we need to double check that assuming laminar was okay. So we're going to use the fact that V is equal to Q divided by A. So our A is pi times D times lowercase a. We have all of these values. So we have 0.147 meters per second is our average velocity. And when we use that average velocity to calculate our Reynolds number, we have rho times V bar times A over mu. This is equal to 0.0375, which is, of course, is very much smaller than 2300. So that means laminar is okay to assume. Okay. All right. Okay. All right, now let's talk about the situation where we have one plate stationary, one plate moving. So we have our same setup as before, essentially, but our top plate is going to move with a velocity capital U. We're going to keep our spacing between our plates to be A, and I'm going to keep my coordinate system down at the bottom again. Okay, so our resulting equations from before still hold. We just need to redo the boundary conditions. All right, so we have that U is equal to 1 over 2 mu partial P partial X. No, sorry, partial Y, no X. Times the quantity of Y squared times Y squared plus C1 make sure I write down the right thing. C1Y plus C2. All right, so this is our starting kind of equation that we have after we did our separation of variables and integration the 2 times. And then our boundary conditions in this case are that U is equal to 0 at Y equals 0. And then we have U is equal to capital U at Y equals A. Okie doke. So this first one is still going to give us that C2 is equal to 0. Right? And let's apply our second boundary condition. So we have capital U is equal to 1 over 2 mu partial P partial X times A squared plus C1A. So I'm going to divide through by A and then move my first term on the right-hand side over to the left. So I have U over A minus 1 over 2 mu partial P partial X times A is equal to C1. All right, and then I can plug that back into here, and I get with some combining of terms. So I'm going to group my terms that have 1 over 2 mu and partial P partial X together. So I have y squared, and then I also have minus a times y. But then I also pick up this u times y over a term as well. And that's it. What?
For the one.
Oh, I divided through by a. So I did divided by a, divided by a, divided by a.
I forgot to, okay.
No, it's all good. I was skipping steps. Fair question. For what it's worth, if you're following along in the books, this is sometimes kind of rewritten in a different way. So this first term sometimes ends up, people will write it with an a squared pulled out front so that you can write the inside as y over a squared minus y over a. This is the exact same expression, just written a different way. Just so you're aware. Same thing. All right. Just like before, we want to know our volume flow rate, our average velocity, and our shear stress. So I'm going to write those results down for you as well. So our shear stress is just mu times du dy. As always, that's just the definition. And so we get mu times u over a plus a dp dx y divided by a minus a half. All right, so here is your definition for shear stress when the top plate moves. We also want our volume flow rate. So as Q over L, so this is volume flow rate per depth. And that is UA over 2 minus 1 over 12 mu dp dx a cubed. The average velocity is just Q divided by A. So V bar is equal to Q divided by A. So this works out to be U over 2, 1 over minus 1 over 12 mu dp dx times A squared. And then last but not least, for a moving plate problem, some interesting things happen in terms of when does the velocity become a maximum inside of there. So point of max velocity if you think back to Calc 1, max velocity is going to happen at wherever du dy is equal to 0, right? So that's how we find maximums and minimums. So this happens at du dy equals 0. So if you plug in du dy equals 0, and then solve for y, just like how you would do in Calc 1, what you get is y is equal to a over 2 minus u over a 1 over mu dp dx. All right, so where your point of maximum happens is highly dependent on what your pressure gradient is doing and whether it's positive or negative or 0, okay? Okay. Yeah.
We don't have to go through
Nope.
the equation every time we just use.
You can use what's in the boxes that I made. Yep. And on the exam, a good way to know whether I want you to do that is I will ask you. So for like a question that's based on topic 4, I'll be like, I will print out for you Navier-Stokes equations and conservation of mass. And one of the parts of the question will be simplify these equations
Okay.
and then derive like what the expressions for velocity will be. For example, it'll be, and if I don't provide you with like the Navier-Stokes equations, you can start from these. Yeah. You can also use these as a good check though, in the event that you need to do something similar on the exam. You kind of know what the end result should be. I still want you to take me on the journey to getting there. But yeah. Yep. Do you guys have the energy for one more example before we take a break? You can do it? Okay. All right, let's do one more. So this is kind of similar to the last one that we did, except for we're going to have some velocity, obviously, because one of the plates are moving up. Okay, so we have a crankshaft journal bearing in a car engine that's lubricated by SAE 30 oil at 210 degrees Fahrenheit. The bearing diameter is 3 inches. The diametral clearance is 0.025. And the shaft rotates at 3,600 RPM and is 1¼ inches long. The bearing is under no load, so the clearance is symmetric. And we want to determine the torque required to turn the journal and the power dissipated. All right. Okay, so we have kind of a similar setup from what we had before. All right, where this is our diameter, which is given to us. This is 3 inches. And this thing is turning with an angular velocity omega. We also have this clearance, which is A. They've given us diametral clearance, which is the clearance for both sides. So A is actually this 0.0025 inches divided by 2, if that makes sense. Okay, so what we want to find in this problem is we are looking for torque, which is T, and then we also want to find the power dissipated. All right, the torque on this journal bearing is caused by viscous shear. So the fluid friction is what's causing it, just like how our viscometer calculated viscosity from experiment 1 or lab 1, sorry. So this is caused by viscous shear. or fluid friction. All right. Our gap width is small, so we're gonna again approximate this as 2 infinite plates. All right, so we have our top plate and our bottom plate. Here is A. This one is moving at U. And then we have our velocity doing something like this. Okay. So I'm keeping my coordinate system just like how we derived these expressions before. And we're going to make all the assumptions that we need to make in order to just jump to essentially the equations that we already derived. All right. So we're going to assume steady, incompressible, fully developed, and we're also going to assume dp dx is equal to 0, as well as laminar. All right, so we were not given any information about pressures on different parts of the system, so we're going to assume there's no pressure gradient. It's a little obscure, but also the statement that the bearing isn't under load could lead us to the dp dx is equal to 0 conclusion as well. And yes, these are all of our assumptions. So since we're after torque, which is caused by viscous shear, we want to figure out what the shear stress is. So we're going to start with tau yx, which is already given to us. We have mu is u over a plus a times dp dx times the quantity of y over a minus 1/2. All right, so I'm just starting from that equation that we derived earlier. This is the final result. We can just start with that. We assume that dp dx is 0, right? So this whole term goes to 0, which is rather convenient for us. So we just have mu times u over a. Yeah. Yes, so this is a great question. So we are looking for torque on the system. Torque is going to be caused by basically the resistance of the oil in this system. So we know that the torque, if you remember back to lab 1, we kind of talked about this, but the torque to spin our little drum in the oil was caused, the torque we needed was related to kind of how much that fluid was resisting the flow. So basically our torque is going to balance our shear stress times the area. So that's the force of the fluid. So yes, that is where we're at. So let me write this down maybe before we get to this point, because I had it in a different order, but I think it probably works a little better this way. So since torque is caused by the fluid friction, our torque is a force times a lever arm. In this case, we're going to use the radius, right? That's just the definition of torque. And this force is our friction force due to the fluid. All right. And we know that this friction force is just our stress. So this is our shear stress from the fluid times the area over the surface where it's acting times R. All right. And we have all of this except for this one. We need to find it. All right. So that's why we're starting with stress. Does that make sense? Or does that help? Okay. Okay. All right, so this is pretty simple. We just have viscosity times our top plate velocity divided by the gap between the two plates. We were not directly given the linear velocity of that top plate though. Does anybody know what it would be given omega? So omega is units per second. So we need to get it into meters per second. So we need a length. Does anybody remember? So this is just omega times r, right? And then we keep r divided by a. Okay. So we have all of this stuff. Viscosity, again, just like the last oil problem, we would look this up in a table. And so when we do that, we have the following. So we have 2.01 times 10 to the minus 4 pounds of force times second over feet squared times omega, which is 3,600 revolutions per minute, times 1 revolution is 2 pi radians, right? And then 1 minute is 60 seconds. And then R is 3 inches, so 3 divided by 12 feet, divided by hold up, hang on. So this is our diameter, but we needed radius, right? So I'm going to do 3 divided by 2. All right. And then we're going to divide by A, which is 0.00125 divided by 12 feet. And we get 90.9 pounds of force per square foot. All right. Torque is tau yx times A times R. So we have tau yx. Our area is just our circumference times the length. So that is the area of kind of the outside of our cylinder. And then times R, which is D over 2. So we have pi over 2 tau yx d squared L, which is 11.2 inches times pounds of force. Any questions on that example? Yeah.
So. In terms of like tau yx.
Yeah.
Going back.
Here?
This was, that's the formula we're using, or is it from the other page of this?
So we're going to use this formula because we have a plate that moves. If the plate were stationary, then we would use this one instead. Yep. I believe I will post this with the example problems, or I'm sorry, the example exam, but on the equation sheet, I have it into sections, like 2 plates, both stationary, 2 plates, 1 moving, so that, it, you know, you have that. Yeah.
Wasn't this equation in topic 1 or 2? The shear stress equation?
It has probably been almost everywhere at this point, but probably. I can't remember where I first did it. Okay, yeah. I believe you. Other questions on this example? You guys have all seen Home Alone, right? Okay. So we're going to talk about fully developed flow in pipes now. So before we did flat plates, Cartesian coordinate system works just fine for flat plates. Once you start thinking about doing pipes, you need radial coordinate system. And so this is what the Navier-Stokes equations look like in cylindrical coordinates. Super fun. That's why but don't worry. I'm going to largely kind of in a hand wavy way go through what happens with these equations. If you visit me in intermediate fluids, we'll talk about it in a little more detail. But I would prefer for this portion to be fairly painless for you all. Not that I want you to be pained in intermediate fluids, but maybe just a little bit. Okay, so in this form of the equations, what we have is a z coordinate system that's going to go kind of along the center line of a pipe. Like so. This is not a great drawing here, but hopefully you get the idea. And then we're going to have our radial direction, obviously, along the radius of this pipe. And then as you rotate around here, this is going to be our theta direction. Okay, so if you imagine kind of what's happening inside of a pipe, we're still going to have this parabolic sort of profile for the velocity. So this is our z component of velocity, which is a function of r. The big difference here is that for a set of plates, this parabola kind of just extrudes in the depthwise direction. For a pipe, it's revolved. So this is kind of like it's a paraboloid. Not kind of, it is. All right. So to compare with our Cartesian system, so in Cartesian, what we've done all so far, we're using u, v, and w as the x, y, and z components of velocity. In cylindrical, we call it ur, u theta, uz. Okay. And when we simplify these equations, we end up with, I'm gonna kind of skip over the simplification and everything. But essentially, I'll show you how these equations simplify, but I'm not gonna go through the whole solving of them. So we're gonna use the same assumptions as we always do. We're gonna say that the flow is steady. So our DDT terms are gonna go to 0. So I can get rid of all of my DDT terms, which is just fine. I'm also going to assume fully developed. So if you go back to our picture of our pipe, the flow is in the z direction. So all of our z derivatives with respect to velocity are going to be 0, and then uz is also going to be 0. So I can get rid of everything with a uz. Here, 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 here. And this, simplifying these equations is a little more delicate because there are these, the directional terms are not separated quite as nicely as they are in the Cartesian system. And then I'm also going to get rid of my z derivatives with respect to velocity. Okay. And then I'm also going to make the assumption that this is one-dimensional flow. So I'm going to say that u is a function only of r. And so that means that u theta is also 0. Kind of the argument that you make for that is theta is a change as you sweep around in a circle. So if you're considering kind of flow through a pipe as you rotate around in the pipe, there's really no reason why your velocity should change in a ring, if that makes sense. So if you go from 0 pi to 2 pi, there should be no change. So I can get rid of all of my u thetas. Of which there are many. And then I'm also going to get rid of changes with respect to theta, kind of for the same reason that I just said. So like when you rotate around a consistent, like R location in theta, you don't expect any changes there. So these are also equal to 0. So I get rid of my theta derivatives. I think that's all of them. Okay, and so the simplified equation of interest is the axial one. So I have d wait, uz is not 0. Yo, sorry, hang on. ur is 0. Sorry about this. The uz ones don't go away. I shouldn't have deleted those. Okay. That should be okay. Okay, and then when we simplify our conservation of mass, we end up with, let's see, I'm gonna do purple. So if you remember in Cartesian coordinates, when we do conservation of mass, like the simplified conservation of mass, we usually get something about impermeable boundaries. So if we look at this coordinate system, our impermeable boundary is going to be the r component of velocity. So the velocity kind of going out radially has to be 0 because we don't have anything leaking out of the pipe walls. So we get that ur is equal to 0. So for that reason, we can get rid of these and this. And that should be it. Okay. Okay, so sorry about that. So our simplified equation of interest is the one in the axial direction. And so we end up with dp dz is equal to viscosity. This ur goes away. Times 1 over r ddr r times duz dr. All right, so this looks kind of reminiscent of what we saw in Cartesian coordinates, but we have this 1 over r and r that are in here. So we have to be a little more careful with the separation of variables and integration. But once you go through that exercise, we end up with the following. So after separation of variables, and integration, I will not ask you to do this unless you take the next class. We end up with uz as a function of r is equal to U max times 1 minus R over R squared. Or an alternative way to write this is UZ of R is equal to partial P partial Z, 1 over 4 mu R minus R squared. All right, so you might notice that if you compare these two equations, this must mean that U max is equal to negative 1 over 4 mu R squared dp dz. All right, but those are both equivalent statements that you may see.
So the one over big R.
Yes, yes. Let me make that more clear. Yeah, that's a little lowercase r. So our little lowercase r is the variable, the radial direction variable, like x, y, or z. And then capital R is the total radius of the pipe. Okay. Okay. We also would like to know the stress distribution in a pipe. And so I'm going to, so in Cartesian, so for our stress distribution in Cartesian coordinates, we cared about tau yx, generally speaking. In cylindrical, we care about tau rz, which in this case is mu times partial uz partial r, which is mu times ddz of partial p partial z, 1 over 4 mu r squared minus r squared, which all works out to partial p partial z r over 2. All right, so this is the shear stress distribution. If we consider the shear stress on a pipe wall, so if we have, this is our pipe, here's our Z direction, here's our R direction. So the surface normal on the pipe wall is going to point away from our surface. And then our shear stress, like this, is going to be tau negative R Z. All right, so tau negative RZ is going to be minus partial P partial Z R over 2. If this is a positive number, that means it points to the right. And if our shear stress points to the right, this means that partial P partial Z must be less than 0, right? To get the two negatives. That was kind of a little aside there. Yeah.
What's that next to the equal sign?
Oh, positive. I'll just write it out.
Oh,
Sorry, that was sloppy shorthand. Positive number. Yeah.
What's that? It's like, it's not the shear stress, it's the one you put it over.
Oh, it's an n hat. So that's like the area normal for that surface.
I was just.
Sorry. Yeah. Yeah, so it's negative RZ because it's pointing in the negative direction to our coordinate system. So our area normal is pointing negatively relative to where our coordinate system would point.
Also, it's based off the normal.
Yeah.
Okay.
Yep. So if you remember in like, was it like topic 1 when we kind of talked about stresses? So this first kind of index on here is for the area normal. And then this is for the force direction. All right, so our force is going to be in the z direction, and then our area is going to be in the negative r. Okay, cool. So this was our stress distribution. We also need our volumetric flow rate. Um, actually, please hold. I have a little bit more to say about this first. Okay, so okay, so I want to make a small note. So when we look at our velocity in the z direction, it looks like this. So we have our pressure gradient times 1 over 4 mu r squared minus capital R squared, right? Okay. So if we look at this coordinate r is always going to be greater than or equal to 0, but always then less than or equal to r, capital R. Right? So if we think of how our coordinate system works, so our coordinate system is centered in the pipe. So at the center line of the pipe, R is 0, and then all the way at the wall, it's capital R. So when we have this term, little r squared minus capital R squared, this is always less than or equal to 0, right? Does that make sense? So it's 0 when you're at the wall, which is good because we would have no velocity at the wall because there are no slip condition. And then it's going to be negative otherwise. Okay. So what this means is that if our pressure gradient is greater than 0, then uz is going to be less than 0. It's going to be a negative number. And if our pressure gradient is less than 0, then uz is going to be a positive number. Okay, so another way to look at that is if we have our 2 points, 1 and 2, if we have P1 is less than P2, then our velocity is going to move in the negative direction. So it's going to go like this. And if our pressure is the other way, so that we have P1 is greater than P2, then our velocity is going to move in this direction. Okay? Which is hopefully intuitive, right? So you can kind of think of pressure as like a driving force here. And so the flow is going to follow what the pressure is doing. Does that make sense? Feels okay to everybody? Okay, cool. Kind of along these lines, let's talk about pressure drop. So we're going to define the term pressure drop. So this is delta P, also called pressure loss. All right, so we have a pipe and we have points 1 and 2. So partial P partial Z is equal to P2 minus P1. And then this is our Z coordinate system goes like this. So we have Z2 minus Z1. And if the distance between these 2 points is L, this is minus P2, or I'm sorry, minus P1 minus P2 over L. So this delta P I'm defining as P1 minus P2. And that's what is the pressure drop or the pressure loss. Okay. So I can use this pressure drop to rewrite our equation for our velocity. So our UZ as a function of R is negative delta P over L, 1 over 4 mu, R squared minus capital R squared. All righty. Yeah. Does it say mu where?
Like, let's see, it's like ours. It's like most right.
Okay, hang on.
Yeah.
Do you mean this? No.
It's next to the capital R squared.
This?
Yeah.
This one?
No, like, I don't know.
Yeah, it kept getting cut off. Hang on. let me write this better. Okay, so I have minus, maybe not, minus delta P over L, 1 over 4 mu, little r squared minus capital R squared. There we go. I knew in my heart that it wasn't clear, so it's good you asked. Okay. So now we have kind of how pressure drop is related to velocity. We've talked about how this intuitively makes sense with the direction of the velocity compared to how the pressure is changing. We can also write down a relationship between the flow rate and the pressure drop. All right, so we have that Q is equal to V times A, or the integral of U dA, which in this case is an integral from 0 to R minus delta P over L, 1 over 4 mu, lowercase r squared minus capital R squared times 2 pi r dr. So in case you're not super up in your cylindrical coordinates, dA is 2 pi r dr. And then this, of course, is u. All right, and so when we do that integration, we end up with pi times delta p over 8 mu times L r to the 4th. And then you can, of course, solve this for delta p as q times 8 mu L over pi r to the 4th. Same equation, just rearranged. All right. Okay, we're gonna skip some pages in here because I blew through that derivation and didn't show you all the details. So we're gonna try an example. Whew. Okay, so it turns out that you can make a simple and fairly accurate viscometer using a length of capillary tubing. So if we measure the flow rate and the pressure drop, and we know the tube geometry, we can compute the viscosity of a Newtonian fluid using the volume flow rate equation. All right, you'll notice that there's a 128 in the denominator of this. That's different from the equation I wrote on the other page. That's because we're using diameter and not radius. So there's a 1/2 that gets raised to the 4th power in here. So do not panic that the equation is different. It's just the difference between radius and diameter. All right. Okay, so we did a test with an unknown liquid in the capillary viscometer, and we got some data. And we want to figure out the viscosity of the liquid. So we are looking for mu. All right, we've been given flow rate. So this is our Q. We're given our tube length. That's L. We're given our tube diameter D, as well as our pressure drop delta P. All right, so we have our governing equation is just that Q is equal to pi times delta P D to the 4th over 128 mu times L. And we want to solve this thing for mu. All right, and so when we do that, we get pi delta P D to the 4th over 128 L times Q. All right, so we have all of these things, so I'm just going to plug them in. So our pressure drop is 1 megapascal, so that's 1 times 10 to the 6th newtons per meter squared. Diameter is 0.5 millimeters, so we have 0.5 times 10 to the minus 3 meters. That gets raised to the 4th power. And then in our denominator, we have 128. L is 1 meter. And then we also have Q, which is 880 cubic millimeters. And then I'm going to convert millimeters, cubic millimeters. Ugh. So there's 1,000 millimeters per meter. We got to cube that to get our units all correct, right? And when I solve this, I get 1.74 times 10 to the minus 3 newtons times seconds per meter squared. All right, that's all well and good. Fairly straightforward. But we're not quite done yet. We need to check that the Reynolds number is low enough that assuming laminar was okay to do, because if you remember, we're still kind of in the mindset of we're assuming all flow here is laminar, so we need to make sure that that's actually the case. So we want to check the Reynolds number. All right, so the Reynolds number is equal to rho V bar D over mu. And we have Q but not V, so we are going to substitute that V is equal to Q divided by A. So here we have rho Q divided by A times D over mu, which we're going to assume that we've been given rho. So this is 999 kilograms per meter cubed times 880 millimeters cubed per second. And then we got to convert that again back to meters cubed per second. So we have 1,000 millimeters per meter. That whole thing is cubed. And then we're going to divide by the area, which is pi times the diameter, which is 0.5 times 10 to the minus 3 divided by 2 squared. And I need more space. Hang on. Okay, times. So this is Q over A times our diameter, which is 0.5 times 10 to the minus 3 meters. And then that whole thing is divided by the viscosity that we found, which is 1.74 times 10 to the minus 3 newtons times seconds per meter squared. All right, and this gives us 1290, which is less than 3,200. So the flow can be assumed laminar. So that was okay. We could use that equation. Wait, did I write it wrong? Was it 2,800? I'm unreliable. I can never remember what it is. I always have to check. So hang on, please hold. 23. Not even close. Thank you. Don't trust me. I'm just kidding. You can trust me, but that was wrong. Thank you. Any other questions on this example? No? Okay. Okay. So that is part A. We talked about laminar flow in pipes and between plates. So you have kind of a suite of equations that you can use. Just be careful on kind of what the conditions are that you have. So check whether it's plates or a pipe. Make sure it's laminar. If one of your plates is moving, for example, you have to use a different set of equations, but generally that's part A. All right. The second part of this is we're going to talk about flow in pipes and ducts. But we're also going to consider some more factors that come into play in real systems like turbulence, roughness to pipes and all that good stuff, inefficiencies. And so to do that, I'm going to start by kind of walking through the energy equations or the energy considerations for flow in pipes. So I'm going to just kind of neglect this statement for a second. So let's talk about energy considerations. For flow in pipes. All right, so if you consider just the energy equation, so we have the time rate of change of energy in a system is equal to Q dot, so this is the rate of heat in to the system minus W dot, which is the rate of work out of our system. If we write this for a control volume, we get the following. So we have that the time rate of change over the integral of all of the energy in our system is equal to essentially the energy leaving. All right. So in words, this means that the difference between heat in, so Q dot, and work out, which is W dot, is equal to the change of energy inside of the control volume and the rate at which energy is carried in or out. All right. So I'm going to just highlight a few things here. So we've got our heat in, our work out. That's awful. And then the change in energy inside the control volume. That's this guy. And the rate at which it is carried out is this. Okay. So if we consider steady flow through a pipe, steady flow through a pipe. So we've got our pipe here. We have 0.1, 0.2. This is, I'm drawing here my control volume. So this is, let me do it in another color. So here's our control volume. All right. And we're going to let our specific energy, our lowercase e, is going to be partitioned into kinetic, potential, mechanical, and internal energy, all the energies that you can imagine. So kinetic energy is V squared over 2. Potential energy is G times Z. Mechanical is pressure divided by density. And then internal energy is just going to be lowercase u, not velocity. All right, and we're going to assume steady. So this means that our time derivatives go to 0, right? Okay, so if we do that, we end up with q dot minus w dot is equal to the integral over the control surfaces of all of our different types of energy. So we have internal energy plus kinetic energy plus potential energy plus mechanical energy times rho v dot dA. And we can, of course, separate this integral into 4 different ones for each of the different kind of buckets of energy that we have. We're going to assume that internal energy, the Z location and pressure are uniform across the area, so we don't have to do the integral anymore, right? But velocity can be non-uniform. Okay. I'm also going to use the definition that m dot is the integral of rho v dot dA. Okay, so we have this guy is m dot. Okay. Okay, so that means that I can simplify this expression to the following. So we have q dot minus w dot is equal to m dot times the internal energy at point 2 minus the internal energy at point 1 plus the integral over area 1 v2 squared over 2 times rho v2 dot dA2 minus the integral at a1 of v1 squared over 2 rho v1 dot dA1 plus m dot g z2 minus z1 and plus m dot p2 over rho minus p1 over rho. So far, so good. Now this equation is not too bad, but we do have these 2 integrals that remain, which are a little pesky. So what is commonly done is we can simplify our velocity integrals by doing something rather convenient, which is the following. So to simplify the velocity integrals, what we can do is we can say, okay, we have this integral that generally looks like integral over the area v squared over 2 times rho v dot dA. And we can say, well, instead of integrating this whole velocity squared situation, we're going to instead say that we'll use the average velocity at that point and keep everything else the same. But since we're using this average velocity, I need to add a correction factor out front. And you might be thinking, what was the point of this? I still have an integral. Well, once we assume that we have this average velocity, that's a constant with respect to the integral, so we can pull it out. And once we pull it out, then all we have left, our integral is just m dot. So we have alpha v squared over 2 m dot, which is much simpler. All right, and then, oh, yes. Yes. Yep, so this is our average velocity. Here and here. Okay. So you might be thinking, okay, great. That's much simpler. We just have an algebraic equation now, but we have an unknown now. What is alpha? And it actually turns out to be simpler than you would expect. So there's two choices for alpha. For laminar flow, what we generally will get is a parabolic profile. So this is laminar flow. It turns out that for turbulent flow, our profile is something that is very nearly uniform. So this is almost uniform. And so that means that we can choose, for a laminar flow, we're going to use alpha equals 2. And for a turbulent flow, we're going to choose alpha equals 1. Okay. Okay, so let's rearrange our energy equation. Okay, so I am going to group. So I'm going to start with this equation here. And I am going to swap out my integrals for this alpha v squared over 2 times m dot. And then I'm going to also group all of the stuff at 2 and all of the stuff at 1 together. And when I do that, what I get is the following. So I have P1 over rho plus alpha 1 V1 bar squared over 2 plus GZ1. So this is all of our stuff happening at point 1 minus all the stuff happening at 2. So we have the exact same kind of form, but at point 2. So I have P2 over rho plus alpha 2 times V bar 2 squared over 2 plus GZ2 minus my W dot over M dot. So I've divided through by M dot as well. And then this is equal to U2 minus U1 minus Q dot over M dot. Does anyone notice anything that looks a little familiar from last week, perhaps? No? Okay, so these first two terms are very close to the Bernoulli equation. But we've added this correction. So we've corrected essentially Bernoulli's equation for if there's turbulence. All right, and then we also have these additional terms that are showing up here. So if you remember Bernoulli equation, we didn't have the alpha 1 and alpha 2. And then these first two terms were just set equal to 0, right? But now we have other stuff. So now we can take into account that there might be work added into the system. So we have a work term. This is our rate of work out of the system. So that is important because if you have a problem where work is being added into the system, so say you have a pump, this W dot is going to be negative, right? Work in will be negative, work out is positive. It's kind of, if you have trouble remembering, it's the exact same as when we had like our V dot A. If you have an outflow, it's positive. If you have an inflow, it's negative. So same idea here. So we have our work term, and then we also have these two terms on the right-hand side, and I've grouped them both on the right-hand side with intention. So this first term here, our U2 minus U1, this is our change in internal energy. So for example, this is like change in temperature due to friction. All right, and then we also have Q dot over M. This is our rate of heat loss. I have grouped the U2 minus U1 and the Q dot divided by M dot terms together because collectively they have a special name. These two terms, when put together, are collectively known as the head loss. All right. And it's denoted with HLT. So the capital T is total head loss. And it's going to describe, yeah, I thought you had a question, sorry. This is going to describe losses from both Q and U. Describes losses from Q dot and changes in internal energy. All right. So you can think of this right-hand side of this equation as kind of losses due to inefficiencies in the system. Okay. So I personally think this equation is pretty cool. We start with something that's very similar to what we had for Bernoulli, which is, if you remember, a very, very idealized way of looking at things. I warned you about not abusing Bernoulli. Don't use it outside of when all those assumptions can actually hold. This equation has a lot more utility, right? So we can take into account what if the flow is turbulent. We can take into account what if work is added into our system, and we can also take into account typical inefficiencies that we might see in a system. Okay. All right. Okay. So this is kind of a restatement of what I've already sort of articulated to you guys, but friction loss is what's referred to as head loss. This quantity represents the irreversible conversion of mechanical energy at section 1 to unwanted thermal energy, which is our difference between U2 and U1. And then the loss of energy via heat transfer. So that's that Q dot over M dot. All right, so another way of saying this is that the mechanical energy, it's the mechanical energy loss due to friction between 1 and 2. Okay. So for pipe flow, I want a different color. Many times W dot is going to be 0. It's going to be 0. But sometimes it's not. So when the system includes a turbine or a pump, we have the following. So we have pressure at 1 divided by density plus alpha 1 average velocity at 1 squared over 2 plus gz1 minus all of that same stuff at 0.2. So our pressure over density plus our correction factor times the average velocity squared plus gz2 plus h pump in. So this is what's called the pump head plus, minus H turbine out. This is the turbine head. And this is all equal to our total head loss. So just to clarify this kind of change in notation, this term here is just another way of writing. So H pump in is equal to W dot pump in over M dot. And similarly, for the turbine term, this one is just the same thing as W dot turbine divided by M dot. Okay. If we assume no turbo machinery, so no H pump, no H turbine. So this is W dot equals 0. We assume frictionless flow. That means that our head losses are going to be 0. And we assume uniform. That means that alpha is equal to 1. We get back the Bernoulli equation. All right, so this is just another way to show you how this equation has a lot more utility than the Bernoulli equation. You can start with it and add some assumptions to it and get back the Bernoulli equation. So if you were going to choose between this one and the Bernoulli to memorize, to bring with you for the rest of your life, choose this one. All right. And then another note about this equation is that it's common to divide the whole thing through by gravity. And when we do that, we get the following. So we have pressure at 1 divided by rho g plus alpha 1 v1 squared over 2g plus, now it's just z1 minus p2 over rho g plus alpha 2 v2 squared over 2g plus z2 plus w dot pump in divided by m dot g minus w dot turbo out over m dot g. And this is going to be equal to our total head loss divided by g, which is denoted with a lowercase HLT. All right, so if you see a lowercase HLT, that just means it's the total head loss divided by gravity. If it's capitalized, gravity is still on the other side of the equation, okay? This lowercase HLT has units of mass. No, it doesn't. This is units of length. Right? So we can check that because we know from doing dimensional analysis checks on equations, we know that all of the terms in this equation should have the same kind of units because we're adding them all together. So we have on the left-hand side, the variable z all by itself, which is units of length. So that means that the right-hand side also has to have those same units, which is length. Okay. All right. Okay. So if we, did I go too fast? You're okay? All right. Okay, so if we want to theoretically evaluate the head loss, what we do is we break down that head loss into major losses and minor losses. All right, so these are the two categories that we're going to care about. Our major head loss is denoted with HL. So just right here. So our total head loss is equal to the major losses plus the minor losses. Also, yeah, okay. I personally dislike this notation just because major and minor both start with an M, and I don't know why minor losses got the M. I can't explain it to you other than just tradition, apparently. So I don't have a good trick for remembering which one gets the M and which one doesn't. It's just, it is what it is. I'm sorry. Okay, so let's talk about major losses first. Major losses are going to be the losses that a fluid takes on as it moves through a straight section of pipe. So this is going to be losses due to just the friction in a pipe, okay? As a fluid moves through a straight section of pipe. And then minor losses, on the other hand, are losses as the fluid passes through fittings or bends or some change in geometry. Okay, so let's talk about major losses first. So this one is a little bit, I guess, simpler maybe because kind of we're talking about the same thing for all the major losses. We're just talking about a straight section of pipe and the losses that it experiences as it moves through that kind of geometry. So a simple one. So if we consider just a straight section of pipe, we've got 0.1 and 0.2. And then I'm going to write down my equation here, my head loss equation. So we have P1 over rho plus alpha 1 V1 squared over 2 plus GZ1 minus P2 over rho plus alpha 2 V2 squared over 2 plus GZ2 plus H pump in minus H turbo machinery out. And this is going to be equal to our major head losses, right? So we have total head losses, obviously on the right-hand side, usually. There's no fittings in this system. It's just a straight section of pipe. So we just have our major losses, okay? We're going to assume, I did not draw it especially convincingly for this, but we're going to assume that the cross-section of this pipe stays the same. So V1 and V2 should be the same because of conservation of mass. So these cancel. V1 equals V2. I'm going to assume that there's also no elevation change in this system, so we can get rid of these as well. And we're going to assume as well that there's no turbo machinery present. All right, so we end up with HL is equal to P1 minus P2 divided by density. Right? If you recall from our discussion about pipe flow, we have this equation that Q is equal to pi d to the fourth P1 minus P2 divided by 128 mu times L. Remember that one that we just derived? So we can solve this for P1 minus P2. Right? And then what I'm going to do is I'm going to substitute this into our head loss equation. I'm going to put this in there. And so when I do that, I get HL is equal to 128 Q mu times L divided by pi d to the fourth over rho. I need to do a little bit more fussing with this. So remember that Q is V times A. So this is V times, the area is a pipe, right? So the area of a circle is pi d squared over 4. All right, so I'm going to substitute that back in here. So I have 128 V pi d squared over 4 mu L over pi d to the fourth rho. Okay, so I can cancel out d squared, and then I'm just left with a d squared in the denominator here. And then I'm going to just rearrange some terms here. So I have L V squared. Sorry, these V's are average velocities. So let me just throw the bar on top. So I have LV squared over 2 times D 64 times mu over rho v bar d. And I've put this grouping in red because it's special, because this is 1 over Reynolds number. Okay. So what we have here is that head loss, major head loss is equal to L V bar squared over 2 times D, 64 divided by the Reynolds number. 64 divided by the Reynolds number has a special name, and it's denoted with the symbol F. It's called the friction factor. Okay. And this whole equation also gets a special name. It's called the Darcy-Weisbach equation. All right, so we have that HL is equal to LV bar squared over 2D times F, where F is equal to 64 divided by the Reynolds number for laminar flow. Okay, so we can only use this expression for F if the flow is laminar. The reason for that is we used this volume flow rate, which if you remember, we derived that assuming laminar flow. Okay, so laminar flow still has to be happening in order for this to be the case.
Explain where you got the circle in red, where you plotted the,
One over the Reynolds number part.
yeah. Squared. All these squared.
The V. Oh, that's a good question. Please hold. Because I was shifty about it. So it's just 1V in the numerator, right? Well, I made it V squared. Ooh. I made this V squared because I'm dividing by V. So I wanted to get a V in the denominator so I could pull out a Reynolds number. So I had to pick up another V squared in the numerator. Does that track? So like we want V bar only. So basically what I did is I said, well, I have V squared divided by V. And that's the same. Very shifty. I know. It's a good question. Other questions? Okay. So hang on, don't fear about that chart just yet. I'm going to add just a page so you don't have to look at it while I explain something else. Okay, so this F equals 64 over the Reynolds number. That's very convenient. That's very simple. But it only works for laminar flow, right? So what if we have turbulent flow? The other part of our equation has that alpha. We can correct for turbulent flow. So we should be able to take into account what happens with the head losses for turbulent flow too. So the question is, what about turbulent flow? So I think I've said this before, but just to emphasize, we can't derive a nice clean algebraic equation really like this for turbulent flows. analytically. I have too many letters here. There we go, that's better. Okay, so I cannot do this analytically for turbulent flows. So what we need to do is we need to use empirical data. All right, and what we know is that the friction factor is going to depend on the Reynolds number, and it's also going to depend on something that's called the relative roughness. So this is relative roughness. All right, and this epsilon that I have in here, you can think of this as if we have a pipe. No pipe is perfectly smooth, right? There's little kind of microscopic bumps in here. So I'm drawing this exaggerated. They're not actually this big, but we have our pipe diameter. And then the average size of these imperfections are epsilon. Epsilon is something that you look up in a table depending on what kind of a material you have and how the pipe was produced. Okay. All right, so we know that our friction factor is going to depend on our Reynolds number. It's also going to depend on our relative roughness. And for turbulent flows, we're going to need to use empirical data, which generally means we need to use a chart to figure this out. Okay, and the chart that we're going to use is called the Moody chart. This is the Moody chart. It looks very complicated on first glance, but I promise it's not that bad. All right. So I want to kind of point out a few things to you about the Moody chart. The first thing is, on the Moody chart is our friend, the laminar flow friction factor. You'll notice it's a straight line, which checks out because we know it's 64 divided by the Reynolds number. So our Reynolds number is on this x-axis down here. So that line right there has a slope of 1/64. I'm sorry, or 60, it has a slope of 64, not 1/64. Okay. Outside of our laminar flow region, we have a bunch of other curves that exist on here. All right, and so these curves correspond to what the friction factor does versus Reynolds number given a relative pipe roughness. So if you'll notice, this vertical axis here is our relative pipe roughness. So this is epsilon over D. So given your material, what you will do is you will look up what your roughness value is. So you're going to find epsilon from a table that looks like this. All right, keep in mind that this is millimeters, okay? So when you're doing epsilon divided by diameter, you need to make sure you're using the same units. So millimeters divided by millimeters, just fine. Millimeters divided by meters, not okay. All right, and once you calculate your epsilon divided by D, then you can figure out where you are on this left-hand vertical axis, okay? Depending on where you are, you're gonna follow a curve around, all right? So for example, if you found that your relative roughness was 0.005, you would be looking at this curve, all right? And the next thing you would do once you've identified your curve is you figure out the Reynolds number for your flow. All right, and then you go to wherever it is on the horizontal axis, trace it up where it meets the curve, and then that's your friction. That's how you find your friction factor. So can somebody give me a Reynolds number that is within the scope of this axis? Can be any number you want. You can make it complicated as well. Actually, please do.
Wait for the 0.05.
So I'm just going to kind of show you how to read this chart, but you need to give me a Reynolds number, somewhere between 10 to the 4 and 10 to the 8. but don't make it like a whole number, please, for the purpose of demonstration.
And to put 5.
Oh, not that one. Can you make it like 5.2 times 10 to the fifth? Okay, great. So let's say, so suppose we calculate that Reynolds number is 5.2 times 10 to the fifth. Okay. My horizontal axis on the Moody chart is a log scale. All right, so I apologize if I'm insulting your intelligence by walking through this once more, but the way a log chart is read is we have decades here, all right? So each of these lines is the following. So I'm gonna go from 10 to the fifth to 10 to the sixth just to show you. So this one is 1 times 10 to the fifth. This line is 2 times 10 to the fifth, 3 times 10 to the fifth, and so on and so forth until you get to 10 times 10 to the fifth, which is just 10 to the sixth. All right. So if we want to find 5.2 times 10 to the fifth, I am looking at 1, 2, 3, 4, 5, and then just a smidge over. So this is my 5.2 times 10 to the fifth. And what I'm going to do is I'm going to draw a line up, all the way up. And I want to figure out where it intersects with my curve for 0.005. All right, so it's intersecting right here. Okay. And we want to find the friction factor that's on the left-hand scale. So I'm going to draw a straight line and trace it over to here. And this is where my friction factor is. All right, so I will also put in here, we have epsilon over D was 0.005. So this means that our friction factor is approximately 0.031. Okay, so when you want to find your friction factor for a turbulent flow, the steps you're going to follow are figure out the relative roughness and figure out the Reynolds number. Once you have your relative roughness, you identify which of these black curves you're going to kind of follow along. Once you find your Reynolds number, you're going to just draw a straight line straight up and you figure out where that curve and your Reynolds number intersect. You identify that intersection point and then go straight to the left to figure out where your friction factor is. So the steps feel okay. It's really not too bad. Just take some practice. Okay. Small note. These curves actually have an equation. So the curves are defined by the Colebrook equation. Which looks like this. So it is 1 over the friction factor to the 0.5 is equal to minus 2 log epsilon over D divided by 3.7 plus 2.51 Reynolds number friction factor to the 0.5. All right, and this is valid for Reynolds number greater than or equal to 2300. All right, so same critical Reynolds number for pipes that we talked about before. I am showing you this because sometimes you might want a more accurate value for the friction factor than this kind of eyeballing that we did here off of the chart where we said, well, it's about 0.031, right? Maybe you want something more precise. You can go ahead and solve this equation if you know the Reynolds number and epsilon over D, but you're going to have to solve it analytically, or I'm sorry, empirically. All right, so MATLAB or similar, you're going to have to figure out that equation because you cannot solve it analytically.
The 2.51 is still part of the.
Oh, it's 2.51. There. A couple of other things that I want to mention, for the relative roughness, you'll notice that several materials have choices on here. So, there's, for example, carbon steel. There's values given in here for if it's brand new, if it's been slightly corroded, moderately corroded, badly corroded. And then, and so on and so forth. You'll also notice that a lot of these have a range of values. And so this is where you'll have to use your engineering judgment. Typically, we want to kind of maybe not necessarily choose a worst case scenario, but depending on the application, if you're interested in kind of baking a safety factor into your engineering design, a worst case scenario is a higher amount of roughness. So, typically you'd want to err on over designing your system versus under designing it. So if you were trying to spec out like a pump for a system, I would suggest picking values on the higher end of this range rather than like the lowest possible value. And then you'll have some extra degree of confidence that the pump you select will work for what you want or need. Okay. Okay. So I think what I still have minor losses to talk about and an example to do. I'm going to save that for next time, I think, if that's okay. So next time we'll finish up the minor losses and do some examples, and then we'll do the exam review. And if as much time is left, I'll go over like essentially like a 2500 review for heat transfer. Okay. Okay.